So this is the end product of the MLFQ, the multi-level feedback queue, and it's actually multi-level. I mean, the multi-level queue is, well, self-describing, right? You will have multiple queues, okay, and each queue will have a priority, and basically within each queue you're going to run round robin. Let us talk about this in more details. So you have multiple queues. Each queue has different priority, and at any given time, a job that is ready to run is only on one single queue. MLFQ will use these priorities to decide which job would run first at any given time. The higher the job priority, the more likely it is going to be chosen to run. You might have multiple jobs in the same queue, so in that case, you are going to use round robin. So these are the first two basic rules for the MLF queue. First, rule number one: if priority A is greater than priority B, then A runs, B does not. Okay, so you run A first, and you do not run B, and you do not run B until A finishes, or for some reason you basically reduce the priority of A. If the priority of A is equal to the priority of B, then you're going to run an round robin. So the key now is how to set priorities. And this is where the whole algorithm is. The whole scheduling part is in that because, well, yeah, sounds about right. That's very easy, but how do I pick the priorities? And how do I make sure that jobs running at queues with lower priority do not get starved? And starvation is basically when you have a job that, I mean, this is not on this slide, I'm just noting. Starvation is when you have a task or job that does not run forever because other smaller jobs or other high priority jobs come into the system and starve your application, basically starve that lower priority task. MLFQ will vary the priority of the job based on its observed behavior. So jobs can move between different queues based on some behavior. Uh, so if a job repeatedly relinquishes the CPU when waiting for input, so basically you start running for 2 milliseconds and then you stop after these 2 milliseconds because you're waiting for input. That's an interactive job where people are typing and you're waiting for whatever they are typing. You're reading data and you're waiting for the data to come and so on and so forth. So if you're basically not using some certain CPU quota, then you might end up staying in the same queue priority queue. Sorry. If instead a job uses the CPU intensively for long periods, then you will downgrade the job to basically run on a less, I mean, a queue with less priority, basically. So you try to predict the future behavior of a job based on its history. So this might be one way to look at it. You have A and B, C and Q4, and D and Q1. And Q1 is lowest priority, Q8 is highest priority. And now you have A and B alternating until they are done. So now if you basically do not change the priorities of A and B and they remain in Q8 forever, that means that both C and D will never run. And if A and B are long jobs, then yeah, tough luck. We now must decide how to change the priorities. Okay, you have to keep in mind that for most computers, you have a mix of workloads. You have the workloads which are interactive, basically user facing, your screen refreshing, your me clicking on my arrow to change the slide. These are all interactive jobs. And there are some that are longer running CPU bounded jobs that would need a lot of CPU time. These are more like if you're running background simulation, some of the security, for example, applications that run at the background that do, if you're doing a disk scan. Actually, if you're doing a disk scan is a very, very bad idea because you're mostly reading from disk. But if you have some of these monitors that consistently monitor your computer, making sure that it's working well. So the first attempt at the priority adjustment algorithm is that when a job enters the system, it is placed at the highest priority, the topmost queue, and if the job uses up an entire time slice while running, its priority is reduced. So you basically specify that, well, any job that is longer than 2 milliseconds or 3 milliseconds will go to the second queue. Okay, that's in priority. And you keep demoting the jobs until basically they reach the least priority queue. Based on what? Based on how long they actually run. This third, well, the continuation on this line of thought is basically if a job gives up the CPU before the time slice is up, so you have an IO bounded job, then it stays at the same priority level. So if you look at this example, you have Q2, and a new job will enter first at Q2, and after a single time slice of 10 milliseconds, the scheduler reduces the job priority by 1, so now it runs at Q1, and after running at Q1 for time slice, the job is finally lowered to the lowest priority queue, which is Q0. So this is the long running job. This is the same job that came in and basically got demoted to Q0. So let me ask, which of the following is this likely to be a high priority job based on what we know up to this point about MLFQ?